Hello everyone. In this chapter, we will talk about weathering, erosion, and mass wasting. First, what are weathering and erosion? What are the differences between them? Weathering is the physical breaking down and chemically decomposing rocks, which include igneous rocks, metamorphic rocks, and sedimentary rocks. The way of weathering can be physical weathering, chemical weathering, and biological weathering. Erosion is physically removing the weathered materials from their original locations. The media of erosion can be water, wind, ice, which are all kinds of fluids. With mass wasting type of erosion, gravity is the primary driver. First, let's talk about physical or mechanical weathering. Physical weathering is just breaking rocks into smaller fragments without changing their chemical compositions. It can happen mostly because of frequent volume changes of rocks. Changing the volumes of rocks can be achieved by switching between heating and cooling, dry and wet, and frosting. For example, water freezes at night and expands because the solid ice occupies greater volume than water. When water seeps into small cracks in the rocks, after freezing, it wedges the rocks apart. This frost heaving requires an adequate supply of moisture. Moisture must be able to enter and the temperature must move back and forth over freezing point. More examples. Precipitations of salt or other types of mineral in between cracks of rocks can also cause physically breaking rocks apart due to the continuous growth of the crystals. Sometimes clay minerals accumulated in small cracks of rocks. In the wet conditions, clay minerals absorbs water and expand the volume, which also causes breaking the rocks apart. Frequent alternating conditions of dry and wet can further break the rock. When buried rocks are uplifted to the surface again, the overburden load is removed and the rock can be broken by the rebound. Another example is exfoliation. Exfoliation is curved plates of rocks are stripped from the larger rock mass. It is caused by stress release and the entry of water. Chemical weathering alters both the chemical and the mineral compositions of the rock. Most of the time, it involves water dissolving gases and reacting with the rock, such as dissolving minerals or part of the minerals to form new minerals. Simple dissolution can be silica oxides dissolved into water, though the solubility is very low. Other times, gases dissolving in water can change the pH of water. For example, when carbon dioxide dissolves into water, bicarbonate ion and carbonic acid keeps the water slightly acidic, which enhances chemical weathering when such water in contact with other minerals and rocks. From here, you may have noticed that chemical weathering consumes bicarbonate and carbonic acid in water, which is formed from dissolving carbon dioxide in the atmosphere. So, weathering of rocks consumes atmospheric carbon dioxide. Let's see the feedbacks of chemical weathering up to climate system. When temperature and atmospheric concentration of carbon dioxide increase, weathering of rocks would be enhanced. The enhancement of weathering consumes atmospheric concentration of carbon dioxide, and this will further lowering the greenhouse effect in the atmosphere. So the temperature will be lowered. Then lowering of temperature and the carbon dioxide concentration will decrease the rate of weathering. So you can see the weathering to climate is a negative feedback loop. Chemical weathering of minerals does not only simply dissolve minerals. Most of the time, acidic solutions dissolve the more components of silicate minerals and form new minerals. For example, feldspar becomes kaolinite after weathering, and some clay minerals become different clay minerals due to chemical weathering. Oxidation and reduction are also important forms of chemical weathering. For example, pyroxene is a common mafic mineral. It is often oxidized to magnetite and quartz. Hydration and dehydration can also change the chemical composition of minerals, and they also happens in chemical weathering. For example, goethite dehydrates to become hematite, and gypsum dehydrates to become anhydrite. So what is the factor to influence the chemical weathering? Mineral itself plays a determining factor. I hope you still remember the Bowen's reaction series from the chapter of igneous rocks. In Bowen's reaction series, we know that the mafic minerals are crystallized at high temperatures, while felsic minerals are at low temperatures. The high temperature minerals are stable at high temperature conditions, but not at low temperatures. So mafic minerals crystallized at high temperatures are more easily to be weathered than the felsic minerals crystallized at low temperatures. To be specific, quartz is the most resistant to weathering among all the minerals. Muscovite is a type of clay minerals. Muscovite is also one product from weathering relatively high temperature minerals. There is also biological weathering. It is the weathering resulted from actions of organic materials, and it is always a combination of physical and chemical weathering processes. For example, lichen, fungus, molds can produce acid that is corrosive to rocks. This picture is taken in Iceland. It is a mold that covers lava basalt. Scientists use this habitat as an analog to study the paleoenvironment where there was no oxygen in the terrestrial plants, to see that how soils are developed when there was no plants on Earth. In fact, growing of plants always provide physical weathering due to the bioturbations from the roots. So, what are the factors that influence the rate of weathering in general? First, grain size matters. Grains with a smaller particle size are of greater surface area and more rapidly react to weathering. Mineral composition determines the mineral's resistance to weathering. Acidic and alkalinic of solutions that interact with the rocks, of course, will influence the rate of weathering. Climate plays an important role. Increasing temperature can accelerate the rate of weathering. Precipitation is the source for most of acidic or alkaline solutions. The availability of rainwater is also the availability of weathering solutions. And on top of that, the type and amount of bioturbations are very important too. So particle size, composition of minerals, acidity and alkalinity of solutions, climate, and the type and amount of bioturbations are all the factors that influence the rate of weathering. The products of weathering include fragments of parent rocks, secondary minerals that formed during chemical weathering, and the soluble ions that are released from the parent rocks during weathering. So there are three types of products from weathering of rocks: fragments of the parent rocks, secondary minerals formed from chemical weathering, and soluble ions that is dissolved in the solutions. Soils are sediments exposed to a stable landscape and experience weathering. the weathering in soil profiles varies. From the soil surface downward, the weathering intensity decreases. In soil, we can also see materials translocate from the top downward to the deeper part of the soil during the weathering process. For example, the topsoil is weathered. Large particles are broken into smaller ones. Carbonate minerals was dissolved. Silicate minerals are partially dissolved and generate clay minerals. The dissolved ions are translocated downward to lower part of the soil, such as carbonate minerals are precipitated in the deeper part of the soil, and the clay minerals are also translocated downward to deeper part of the soil and form soil horizons that are carbonate-rich and clay-rich. In this process, water is the media of translocation. The weathering process in soil is relatively fast is because the particle in the soil is relatively small and the organisms living in the soil provide bioturbations to accelerate the weathering processes. What influences the formation of soil? Climate influences soil formation. High temperatures and precipitation in warm climate can increase the rate of weathering, and low temperatures and small amount of precipitation in cold climate will decrease the rate of weathering. The bedrock material determines the resistance of material to weathering. A bedrock that is mostly sediments originated from lava basalt, which is dominated by mafic minerals, would take less time to weather than that is mostly sediments originated from sandstone, which is dominated by quartz, when other conditions do not change. Another factor is land stability. Soil is full of clay. Clay minerals are from weathering. To accumulate large amount of clay, the sediments in the soil need to stay put for a long time, which means that the landscape is stable and the sediments can stay at the surface without being eroded away to becoming finer particles and adding clay minerals to the soil. Forming soils typically taking 2,000 to 10,000 years. It takes longer when the climate is cold and dry, and takes a shorter time when the climate is warm and wet. Under uniform conditions, the longer it is, the more mature the soil would be developed. So that is all about weathering. Now let's take a look at erosion again. We mentioned that erosion is removing sediments from their original locations due to gravity or different types of fluids, such as wind, water, and glacier. Mass wasting is the erosion of large amount of material in a short period of time due to gravity. Materials have their own angles of reposing. It is the maximum angle at which a slope of loose material will lie without cascading down. The higher the reposing angle is, the less likely the material tend to collapse. Proper amount of water can increase the reposing angle for the material, while too much water, such as a saturated condition, can decrease the reposing angle significantly. This is the reason landslides often happens after storms. Steepness of the landscape also influences the mass wasting. For steeper land slope increases the probability of mass wasting. Okay, that's all about weathering, erosion, and mass wasting. See you next time.